Hello everyone. In this video we are going to learn all about flownets as a tool for performing seepage analysis. So as we learned in our lecture on the governing equations, flow through porous media is controlled by a governing differential equation. And there's a special form of that if you assume that kx is equal to ky, and if we're dealing in two dimensions, that governing equation simplifies down to what is called the Laplace equation. So the second derivative of head with respect to h plus the second derivative of head with respect to y equals 0. And it turns out that in addition to a numerical solution or an analytical solution, we can generate a graphical solution to this equation simply by drawing a set of lines or curves, which are a combination of flow lines and equipotential lines. And so here's a simple example problem. In this case, we have a partially penetrating sheet pile. And the yellow zone is soil, saturated soil. We've got a pounded water on the left and on the right. So the water is, if I use my cursor, the water is basically flowing down underneath the sheet pile to the other side. So the first thing we do when setting up a flow net is we determine our boundary conditions. And so we end up creating flow lines and equipotential lines. So a flow line is a line that the water flows parallel to. So it turns out that the edge of this sheet pile, as you go down one side and up the other side, that's a flow line because water is going to flow parallel to that. And then down at the bottom here on this impermeable boundary we have on the bottom, that's another flow line because the water will flow parallel to that. It will not cross that boundary. Now, on the upstream side, where this ponded water meets the saturated soil, that is an equipotential line because everywhere along that line, the head is the same. Equipotential means equal potentiometric head. So, equal head. It's like a contour of hydraulic head. And then on the right side, when you get to the other end, there's another equipotential line. Then what we do to construct a flow net is we follow some basic rules that we'll talk about in a minute. And you create a set of equipotential lines. And these equipotential lines are basically contours. It's kind of like contours on a topo map. So we start out at this high head value here. And then as the water goes down through here, you lose head. You go from one head value on the left to a smaller head value on the right. So these lines are basically contours of how that head is lost as you move from the left to the right. And then once you've generated a set of equipotential lines, oh, by the way, so this shows that everywhere along that this second equipotential line, this being the first, if you were to put a piezometer at any point along that, the water would rise to this same height. And it would be lower than this value because by the time you get to here, you've lost that much head. And in this case, we have 1, 2, 3, 4, 5, 6 equipotential drops. So by the time you get to the first equipotential line, you've lost 1/6 of the head, the total head that you would lose going from the left to the right. Okay, the next thing you would do is then you would draw a series of flow lines which are drawn perpendicular to the equipotential lines. And these flow lines represent the flow directions, so the flow would be parallel to these lines. And they're drawn in such a way that you generate a series of square cells. I say square, but I mean roughly. They're equal length to width ratio. And in the end, this combination of flow lines and equipotential lines represent a graphical solution to the governing equation. And we can use this solution to figure out what the total head and pressure head would be anywhere in this domain. You can also use it to calculate the total amount of water that will flow through this system. We'll go over how you do that. And so back in the day, before numerical models were a big thing, this was the standard way to solve a seepage problem, was to draw a flow net. We don't generate them from scratch as much as we used to, but it's still a common way to represent a solution, even if later in this semester we're going to learn how to use the SEEP2D finite element program to solve seepage problems. And when we do that, we are going to, the output from that finite element model will be a flow net that we can use to present the results of that solution. So studying flow nets, understanding how they work, how to interpret them, is really important in the context of seepage analysis, and so that's why we cover it. Okay, here's an example of one-dimensional flow. So assuming we had like some rectangular section of soil that was bounded on the top and the bottom, we could draw, since it's one-dimensional, we could subdivide this into 3 flow channels using these 2 interior flow lines. And then if you were to draw a set of equipotential lines such that you have squares here, then we have a solution. Now, you could solve this problem using Darcy's law, but this just goes to show how you can very quickly set up a flow net for simple problems. All right, the rules for constructing flow nets are flow always occurs in the direction of maximum drop in total head. Therefore, your flow lines and equipotential lines should always intersect at 90-degree angles. So 90-degree angles between those 2 families of curves. That's rule number 1. Rule number 2, cells formed by the flow lines and equipotential lines should have a uniform length to width ratio. And generally, that is an equal length to width ratio. So I say squares, but they're squares or distorted squares a little bit, as shown on here. So those are the 2 basic rules. And since each pair of flow lines is a flow channel, the flow through that channel would be, if we look at Darcy's law, Q equals KIA, K, which is K times delta H over L. So if we're looking at cell number 1, so we're looking at this cell right here, and then this cell here. So we're looking at these 2 cells that are in the same flow channel. Since they're in the same flow channel, you'll have the same amount of water flowing through each of those. And so we can set their Darcy's law KIA equal to each other. And then if the drop in head is the same over those 2, so delta H1 equals delta H2, then if we just plug delta H into that and divide by K, divide by delta H, then we get B1 over L1 equals B2 over L2. So this is a mathematical proof showing that in order to satisfy Darcy's law and the assumptions we've made, those B over L ratios have to be equal. Okay? And another way to look at that is so we looked at that that first derivation was based on two cells in the same flow channel. Now if we look at two cells within the same equipotential drop, so B1 and B3, we can do a similar thing. Q1 is equal to K delta H1 over L1 times B1. We can multiply a 1 to get the area because we're assuming a unit thickness in the dimension perpendicular to the screen. Q3, likewise, we have B3 and L3, but they both have delta H1 because it's the same head drop. And then if Q1 is equal to Q3, we can set these two equal to each other. And once again, divide by Q, divide by delta H1, and once again we get B1 over L1. So in order to, based on the concept that there's an equal equipotential drop for cells in the same drop, or for cells in the same flow channel, they have equal flow. Either way, we end up with this B to L ratio must be constant. So that these two things together are a proof of the concept of, this is why a flow net works. This is how a flow net, but simply by having those flow lines and equipotential lines create cells that have equal length to width ratio, we've basically satisfied the governing equation, which is, it's a pretty cool thing. It's a really simple solution to an equation, and so, yeah, so in other words, in summary, if you draw the flow net such that each of the squares have the same length to width ratio, you'll have the same amount of flow in each channel, and all of the equipotential drops will be equal. So, now another way to visualize this is if you have equal length to width ratios, then you would be able to put circles inside each of these cells, and the circles would just touch each side. Now, by the way, how do you go about drawing a flow net? Well, you can draw it on a piece of paper and with a pencil and eraser, and then just keep adjusting those lines. Personally, I like to use the drawing tools in PowerPoint to draw these curves. It's actually pretty quick and easy to do that way. And we'll be doing some of these in our in-class exercise associated with this lecture. Now, in order to, let's say you start out with your flow channels, and then you start making your equipotential drops so that you have equal length to width ratios. It doesn't always come out evenly. I mean, sometimes it does approximately, but sometimes you end up with a partial drop, and there's nothing wrong with that. That partial drop can be somewhere in the middle. It can be on either side, but as long as, except for that one drop or that one channel, and maybe you have a full set of equipotential drops, but you have a partial flow channel, that works as well. But that's not a problem at all. Sometimes, what do you do if you have non-square elements? This is a cofferdam, maybe an impermeable barrier on top of a soil cofferdam, and up here at this corner and down here at this corner. This is an equipotential line. This is a flow line. Just by nature of the geometry, it doesn't quite work out, but that's okay. As long as you still preserve this equal length to width ratio concept we talked about, everything's fine. And if you want to do a test here, if you draw a line that bisects this, it should, if you have equal angles here, it should bisect this line over here. So that's a little test you can do for that particular case. And everything that we've shown so far is a confined problem where it's fully saturated. What do you do if you have unconfined flow? Well, unconfined flow problems are a little more challenging. First of all, you have to guess at the location of this phreatic surface, which is the top of your saturated zone as you're going from the left to the right. And you kind of have to iterate. You have to remember that this line of seepage up here at the top, this top line, it's both a flow line because the water flows parallel to it, but it's also a line of zero pressure because the total head is equal to the elevation head everywhere along that line. So if you want to test to see if your line of seepage is correct, if you draw a line that intersects the location of where your equipotential lines reach that free surface, those should be equally spaced vertically. Because remember, as you go from here to here, that's one drop. From here to here, it's another drop. And then right there at this line, the head is equal to the total head is equal to the elevation head, and so you should have equal elevation drops all the way along. So again, these are a little more challenging. I've personally developed a bunch of flow nets graphically using unconfined flow. It's a lot easier with confined flow, but again, that's how you would develop these and interpret these. And also, where that free surface intersects the upstream side, it comes in at a right angle. Because again, this is an equipotential line and this is a flow line, so it has to intersect at a right angle. Now that's not necessarily true where it comes out at the end, but it is where it comes in. Now, once you have your flow net constructed, there's some fun things we can do with it. We'll talk later about calculating flow rates, but you can use it to interpret things like pressures and interpret how the heads and the pressures vary throughout your saturated zone. And so for this particular example, the total head loss as you go from left to right is it starts out at 40 on the left. Using the base down here as our datum, the head along this line is 40 feet because that's the height to which water would rise. And then on the right side, this region right here is the saturated soil. It's the same problem we started out with, and it has free water, 10 feet of water. Actually not 10, there's some amount of water here above it, and there's a 10-foot head difference. And so this measured relative to our datum, which is the base, that's 30 feet up. And so 40 minus 30, we've lost the total head loss, delta HT, as you go from left to right through this system is 10 feet. And how many equipotential drops do we have? So if you go from here to here, that's 1, 2, 3, 4, 5, 6. So there are 5 internal equipotential lines, and if you count the ones on where you start and where you end, there's NE represents the number of equipotential drops. So there's 6 drops, and so what that means is the head loss for each drop. If you take the total head loss and divide it by the number of equipotential drops, we get 10 divided by 6, which is 5/3 of a foot. And again, the best way to think of these equipotential drops is they're like contour lines on a topo map. And in this case, the contour interval is 5/3 or 10/6 of a foot. And so, yeah, so every time you go down from one equipotential line to the next, you drop 10/6 of a foot. So if we want to know what the head is at point A, we say, well, right along this line right here, the head is 40 feet. By the time we get to A, we've lost 1 equipotential drop. So we do 40 minus 1 times 10 over 6. And we get 38 1/3. So that's what the head is at point A. At point B, we have 1, 2, 3 equipotential drops. That's right on the tip of that sheet pile. So 40 minus 3 times our delta HI, and we get 35 feet. And at point C, This one is a little trickier. We have 1, 2, 3, 4.5 equipotential drops. So 40 minus 4.5 times 10 over 6, we have 32.5 feet is the head at that point. Now for point C, if we want to know what the pressure is there, the pressure head at C is equal to the total head minus the elevation head. The total head is 32.5, the elevation head is 5, so the pressure head at point C is 27.5. If we want to get the pore pressure at point C, it's equal to the pressure head times the unit weight of water. 27.5 times 62.4, we get 1,716 pounds per square foot. So there are a lot of things that we can interpret from this flow net. Another thing that people use these a lot for is to look at the hydraulic gradient. And the hydraulic gradient is the head loss, the change in head divided by the length of flow. So if you're looking right next to the sheet pile, if you measured that distance and took your equipotential drop divided by that length, that would be the average hydraulic gradient there. And as you go down, these lines get closer together, so you get a larger gradient, and then down here you get a much higher gradient, which means most of the flow is going right, or as the water flows around here, these channels get really small, and so you get a higher seepage velocity. And if there's going to be any scour or problems, it would probably occur right next to that tip. And so that again, once you have a flow net, there are a lot of things you can derive from that, and you can gain just by looking at it or by scaling numbers off of it.